The historical gold standard for evaluating policy looks a lot like a mechanical assembly line. It assumes that if you introduce perfectly controlled inputs, you can isolate the variables and measure a fixed predictable output at the end. This linear model relies on establishing a strict counterfactual. By separating a treatment group from a control group, evaluators attempt to prove that a specific intervention was the sole cause of a specific result. But this rigid standard begins to fracture the moment it is applied to the messy reality of a complex adaptive system. Unlike an assembly line, social systems are made of components that interact nonlinearly. People, groups, and markets don't just receive inputs. They adapt, learn, and self-organize the moment an intervention is introduced. Evaluating a living network with tools designed for a machine creates a structural mismatch. If the design fails to account for that adaptation, it risks producing a report that bears little resemblance to how the policy actually functions in the real world. This challenge isn't just theoretical. It is a formal recognition within government that traditional, linear evaluation models are failing to provide the insights modern policymakers need. In 2020, the UK government published a supplement to the Magenta book specifically for handling complexity. It serves as an official framework for moving past outdated, rigid models. The guide outlines 3 specific structural hurdles that complex systems create: the difficulty of setting boundaries, the breakdown of direct causality, and the reality of continual change. To meet these challenges, the focus of evaluation has to shift. We have to move from trying to measure a policy in a vacuum to understanding how it behaves as part of a wider, reactive network. To build that new framework, we first have to deconstruct exactly why the traditional counterfactual model collapses when it meets complexity. The first major failure point is boundary vulnerability. To see this in action, we can look at a common flaw in experimental design. An evaluator draws a strict boundary isolating a treatment cluster from a control cluster. But in complex systems, connections are invisible. Resources bypass this box entirely. In one case, the control group received alternative support from outside the experiment's assumed scope. This leakage across the boundary contaminates the baseline. It makes it impossible to know if the control group is actually a reliable point of comparison. In a simple environment, variables are few and boundaries are easy to maintain. But policy doesn't happen in a simple environment. In a complex system, omitting even one interconnected factor can have a nonlinear impact on the final result. If these hidden influences are ignored, the evaluation's final conclusions may miss the actual drivers of change entirely. When the interconnections are this deep, a clean control group is often an illusion. This leads to the second failure, the collapse of standardization. To mathematically prove that A caused B, an experimental design requires that A, the policy, remains identical every time it's applied. But watch what happens when a single standardized policy input deploys across different local environments. Local context immediately alters the intervention. The policy in cluster A is no longer the same as in cluster B. These contextual reactions lead to wildly unpredictable outcomes. Because the causal chains in these systems are so long and interconnected, demonstrating a direct link between the initial input and the final impact becomes nearly impossible. There are also levers and hubs, highly connected individuals or specific regulations that can disproportionately speed up a policy's adoption or block it entirely. Furthermore, emergent feedback loops can take hold, either suppressing the intended change to keep things as they are, or amplifying it far beyond what the policy intended. When the local environment has this much power over the input, the search for a simple cause and effect relationship hits a dead end. The final failure mode is the assumption of a static end state. Traditional evaluations often assume that once the funding stops or the observation window closes, the system has reached a final, stable result. But a complex network is never truly finished. It continues to shift, pulse, and autonomously reorganize long after the evaluators have left the room. Many systems adapt to maintain their status quo. A policy might look successful during a short evaluation window, only to see the system regress to its old state the moment the external support is withdrawn. We also have to consider domains of stability. A system might seem unchanged for years until it hits a tipping point, leading to a rapid, irreversible slide into a new state. Even the act of evaluation itself can be an intervention. The system might change its behavior simply because it knows it's being watched. If the objectives of the system shift while the evaluation is running, a rigid, pre-planned data collection framework will end up measuring things that no longer matter. In this sense, evaluating a complex policy is like trying to measure a moving target that changes direction the moment you try to focus on it. If these are the ways the old model fails, the question is, how do we build a model that actually works? It starts with alignment. Evaluators must match the core purpose of their study to the specific attributes of the system they are trying to understand. For a new, complex policy, the primary goal shouldn't be to prove a final impact right away. It should be to prioritize learning and adaptive management so the policy can evolve. This framework plots the evaluation purpose against the system attributes to determine which tools are actually appropriate for the job. Randomized controlled trials are still useful in this small, simple quadrant. But as the system attributes become more complex, we have to move into a much larger territory that requires a different set of analytical tools. This matrix helps a team decide whether they need to deploy configurational approaches, system mapping, or computational modeling to get the answers they need. There is no single correct tool. The approach must be as dynamic as the system itself. When we face multiple nonlinear causes, we can use configurational approaches. Instead of trying to isolate one single variable, these methods identify the specific combinations of factors that together lead to a successful outcome. To navigate long, indirect causal chains, evaluators use qualitative system mapping at the very beginning of the process. This often involves participatory mapping, bringing in local stakeholders to help identify the feedback loops and behavioral hubs that a distant evaluator might miss. These early maps are treated as theories to be tested. As the evaluation progresses and new properties emerge, the framework is updated to reflect reality. These methods are resource-heavy and require specialized expertise. But in an unpredictable environment, they are the only reliable way to track how change actually happens. Complexity-appropriate evaluation stops looking for a simple yes or no. Instead, it builds a living, breathing map of how a policy survives and adapts in the real world.